Okay, cruising right along. I think we've set the groundwork. This weird gravitational field energy, the universal version of it, when objects are crazy, crazy far apart, that's so much energy that they don't influence each other. We're going to call that the zero energy. And when they're closer together and do influence each other, because gravity is an attractive force, they're trapped, and the gravitational energy ends up being a negative number. So hopefully you can wrap your brain around that and start buying into that. The math of this, there's only one proof I can find for the proof for this universal gravitational field energy. And good news, bad news, the proof requires calculus. I can't find another proof that doesn't do it without using calculus. So late enough in the school year, if you've already taken calculus, then you should definitely watch this proof, and it'll hopefully reinforce what you learned in the calculus course. If you haven't taken calculus yet, or you're taking calculus now, then you should also watch the proof. There's going to be some weird stuff coming at you in the proof. Just sort of pay attention to it, file it away, and then when you get to learning it in calculus, there'll be like an aha moment. They're like, oh yeah, that's that crazy video I watched for Volek way back when. So definitely everybody should watch the proof, but depending where you're at with calculus, it will make more sense or not make sense. But like any other proof in this course, the proof isn't important. I'm not going to ask you to memorize it, repeat it, regurgitate it. You just need to be able to sort of follow along with it to a certain extent and work with the outcome. So watch that video. Go do that right now. Pause this one, go watch that one, then come back to this one. All right, I'm going to keep talking, assuming you watch that video. The outcome of that video is gravitational field energy. The equation for it is E for energy, subscript G to represent gravity, negative GMM over R. Our equation for gravitational force, universal one, is Fg equals GMM over R squared. If we want to know how powerful gravity is on other objects, we use GM over R squared. Our new equation for energy shouldn't surprise us. It's similar in form to those equations. It's got the G, the constant for gravity. It's got the M's because it's all about mass. Distance is important, so it's got the R. So hopefully it's not too surprising. It's negative GMM over R. Hopefully you're not surprised that it's got those things in it. I kind of talked about it in the previous videos, but another way to think about this new gravitational energy is it tells you how trapped little m is because of big M's influence. The bowling ball, when it's by the birds, it's going to have a huge negative gravitational field energy because that bowling ball is really trapped. It would take a lot of work to get that bowling ball from here up into outer space where the gravitational force has dropped to zero, as opposed to the bowling ball that's by the space station. It's still going to take a lot of work to get it from by the space station to where gravity's influence drops to zero, but since it's already partway up, it's going to take less work from this position than it did from by the birds. So that means in this position, its energy is less negative, which actually means greater. Hopefully this is clicking. It is a little bit weird. Sometimes it clicks better when people do math. If I make up some numbers, let's say the bowling ball weighs, it does weigh about 5 kilograms. Let's say the International Space Station, it's roughly 400 kilometers above Earth. Based off of those two numbers, and because we know the mass of Earth, and because we know the radius of Earth, we can plug and chug, and we can find out how much energy the bowling ball would have when it's way up there. You try it, negative GMM over R. The video's there. One little trick is the R is the distance from the center of Earth, so you've got to take the radius of Earth and add the 400,000 meters. That's got to be in meters, and you're going to get a crazy large negative number, emphasizing that the bowling ball is really, really trapped. What that's telling us is if for some reason we want to take that bowling ball and have it escape Earth and go into deep, deep, deep outer space, it would take that crazy large amount of energy to get it out of there. For fun, if we use that G equals negative GMM over R for the bowling ball sitting on Earth, we're going to get another crazy large negative number. to compare, let's type down here, the answer to the first one, when the bowling ball was up high by the space station, the number that you should have got if you did it, or in the video if you watched it, the number I got was negative 2.9 times 10 to the 8 joules. That's negative 290 million joules. If we do the same calculation when the bowling ball is on Earth, we get another ridiculously large negative number, negative 3.1 times 10 to the 8, negative 310 million joules. Those are both huge, big negative numbers, but the fact that the one at the space station, the negative 2.9 number, is less negative than the other number means it has more energy when it's by the space station. We'll do it a couple times in the course where we need to figure out the work to move something. Work done is always equal to the change in energy. So if we're taking the bowling ball from Earth and lifting it to the International Space Station, we can figure out the work it takes. We just have to take the energy, the second energy, which is the space station height, take away the first energy, which is the height on Earth, since it started on Earth, ended up at the space station. If we do that, notice we get a positive number. 2 times 10 to the 7, that's 20 million joules. If for some reason we had a bowling ball on Earth and we wanted to lift it all the way to the International Space Station, we would have to do 20 million joules of work on the bowling ball. Or if we flipped it, if the bowling ball was already up by the International Space Station and we let it fall, as it fell, again, bad assumption, no heat, as it falls, it would give 20 million joules of energy back to the hole puncher. Hopefully that helps wrap your brain around the math. Negative GMM over R, the R is always in meters and the distance from the center of Earth. The less negative really means the more energy that object has. And when we're comparing, we either compare it to the zero energy that it has when it's in deep, 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 deep outer space, or we do a subtraction to compare how much energy something had relative to another position. I'm going to do one more pause, one more video, and then I think that wraps up this whole big topic.